In this video, we're going to review the law of at least one, also known as the false positive equation. That equation is here, where P is the probability of at least one event, often considered the probability of at least one false positive in a set. And that probability is equal to 1 minus alpha, and that alpha is the same significance level as appears in hypothesis tests, and we'll see how that relates a little bit later. So 1 minus alpha raised to n, where n is the number of opportunities for an event to occur. And if some of that terminology sounds familiar, like we have a number of attempts and we're looking for a probability of a certain number of events happening out of those opportunities. So if that all sounds kind of like binomial equation stuff, you are exactly right. This law of at least one, the false positive equation, is really just a shortcut for applying the binomial equation under the specific circumstance that you want the probability of at least one thing happening. If you were to correctly apply this equation and correctly apply the binomial equation, you would get the exact same answer. Let's go do a quick application, just as a reminder. Here we have 7 days of a week, so 7 different dinners. And we have a picky kid who only likes 10% of the dinners that are cooked for them. And so our frustrated families, or family members, frustrated cooks, want to know what the probability is that our picky eater is going to enjoy and eat at least one of the dinners that is made for them. For dinner number one, this is pretty straightforward. So one dinner at a 10% chance gives us a 10% chance that the picky eater will enjoy and eat their dinner. For dinner number two, on the second dinner, that probability jumps up to 19% by following this equation. 1 minus the alpha level, which we set as 0.1. And we raise that to the number of dinners. So this is the second night, so there were 2 dinners. So there's a 19% chance that our picky kid eater is going to enjoy either dinner number 1, or dinner number 2, or dinner number 1 and 2. So there's 3 possibilities. The probability increases, or the probability of the kid liking at least one of the meals increases when we have 3 dinners, so it increases to 27%. That 1 minus and the 1 minus the alpha level, that all stays the same. And now we raise that to the power of 3, because this is night number 3, 3 dinners. So now there's a 27% chance that our picky kid eater is going to like either dinner number 1, or number 2, or number 3, or 1 and 2, or 2 and 3, or 1, 2, and 3. So we can see as we keep adding more dinners, there's more and more combinations, or really more and more permutations to liking dinners, and so that's increasing our probability. Up until dinner number 7, where there's a 52% chance that our picky eater will enjoy at least one of the meals. Now note, even though this keeps going up, if we were to extend the number of dinners to infinity, the probability would arbitrarily get close to a value of 1, but it would never actually reach 1. So it's never totally certain that something is going to happen. So that's a somewhat generic example on how to apply the law of at least one, or how to apply this particular equation. In reality, that is not what we use this for. We don't calculate probabilities of kids liking dinners. Rather, the place where this equation tends to be used the most is in hypothesis tests. And really, it's an example of when you should not use hypothesis tests. So we can imagine an example here where I have 4 different groups, A, B, C, and D, and I want to do a series of t-tests. So we learned about 2 t-tests, a paired t-test and a Welch's t-test. In this case, I have different individuals in each of the groups, so they are not paired. So I would be doing a series of Welch's t-tests. And all t-tests compare the means of groups. So in t-test number 1, for instance, I might compare the mean of group A to the mean of group B. And ultimately, I'm asking the question whether or not the distribution of data from group A is different from the distribution of data in group B. I've kind of outlined that here. In fact, let me go put an A here. So this will be our group A, and in purple, this is our group B. So we're not actually going to conduct the hypothesis test. Welch's t-test has a very ugly equation for degrees of freedom. That's what online statistics calculators are for, if you ever have to do it for real. But I did want to demonstrate in particular where this alpha comes into play and why alpha is in that equation. So here we have a distribution of data, a distribution of observations, and there's our sample mean from group A, and there's our distribution of data from group B, and our second mean. When it comes to a t-test, we're asking the question whether or not B, or group B, is different from the group A. And we're going to define it as being different by using the same idea of rejection regions and critical values that we have been using for our hypothesis tests. So we will define a critical value related to this group A. Let's go start there. So we have group A, we have a mean, we have a distribution of observations. Let us create this critical value such that the area under the curve here that I've highlighted has a certain probability, or it equates to a certain probability, which is our alpha level. So we're going to go back to our generic 0.05. So the area under the curve here, our rejection region, is 5% of the curve as defined by this critical value. So we're going to say that group B is different from group A if the mean of group B falls in this rejection region. So if the mean of group B in standard deviation or standard error units is greater than the critical value, so again falls in that rejection region, then we will say group B is different than group A. It is too unlikely for the mean to be this high if the data were to all come from this distribution. So if the true mean of group B was actually the same as the mean of group A, then we would not expect the mean to be this far out. Now that said, there is still a 5% chance that a value falling in our rejection region does come from x1. So we see the curve here is still in red. So even the data out here is still part of this group A distribution. And so we have set ahead of time via this alpha level, there's a 5% chance of seeing something this high, even though it still actually comes from group A. That 5%, that's our false positive rate. And it is specifically a false positive because we're saying group B is different than group A, our positive part, but that's false because it actually is part of group A. Make sure I said that right. We're saying that group B is not the same as group A, positive, but that is false because it actually is part of group A. So that is how that alpha level, and why we actually do call that an alpha level. And really, again, it's kind of true application in statistics. So if we do this first hypothesis test of group A versus group B, there's a 5% chance that we're going to get the wrong answer. If we say that group B is different than group A, again, 5% chance that we're wrong. That is our false positive rate. So for our first test, A versus B, in the same way that we just plugged in alpha over here, we can plug alpha in over here. Or perhaps it's better just to go stick with the equation. 1 minus the alpha rate raised to the power of 1, because we've only done one hypothesis test so far, still gives us the alpha rate. Well, now we want to do another comparison. We're going to take group A, the mean of group A, and compare it to group C. So theoretically, this kind of works the same way. Instead of a B here, we'd have a C here. So there's still a 5% chance that if we see a difference, because our second mean is in the rejection region, that it didn't actually happen, that it is again a false positive. And now we have 2 opportunities for that to happen. So we are 1 minus, open parentheses, 1 minus the false positive rate raised to the power of the second test. So that was test number 1, this is test number 2. So it's just like dinner number 1 and dinner number 2. So now we're there, and we can kind of see what's happening. So if we do a third test, group A compared to group D, then it is 1 minus 0.05 raised to the power of our third test. And so if we keep going up, yeah, I think we'll just have to do this by hand. Then 1 minus 0.05 to the 4. A little faster if I just do it this way. There's 5, and there's 6. So we can see, so we did group A to B, A to C, A to D, B to C. So we're just doing all the permutations here again. Sorry, combinations, because order doesn't matter. So once we do all of those combinations, we can see by doing multiple comparisons, there's a 26% chance, based on that alpha level of 0.5, there's a 26% chance that at least one of those tests is going to give us the wrong answer. That's the, in part, that's the real take-home message, and where we really start caring about this equation. When we start getting numbers like a quarter, a 25% chance of us getting the wrong answer by doing these multiple comparisons, it indicates that we really should not be comparing multiple groups in this way. And in fact, we did not get into it in this class, but there is a hypothesis test called an ANOVA, an analysis of variance, that does multiple comparisons all at once, specifically so we do not have to do these multiple comparisons and we don't get this really huge false positive rate. Yeah, so hopefully that made sense. And again, this kind of please avoid multiple comparisons being the real take-home message and the true application to the law of at least one and the false positive equation.